Okay, let's try to systematize a little bit the molten salts just qualitatively here. So I'm dealing here with this whole series of molten salts, ACl, MCl2, where A is an alkali and M is a divalent cation. Okay, so what we see is that many of these salts for all different values of M, for cobalt, iron, nickel, and so on, we tend to have this same type of behavior with quite strong ordering around the 33% composition, which is the M2, alkali 2, MCl4 thing. So as I said, in the basic region here, a simple way of treating it is to look at complex MCl4 anions. Better and more complete way of doing it so that you can treat the whole system and so that you can fine tune and optimize the thing is to treat it as a quasi-chemical model between the second nearest neighbors. Second nearest neighbor MM pairs plus the second nearest neighbor AA pairs gives you two second nearest neighbor AM pairs. These are A's out here. Okay. And if this delta G of this reaction is strongly negative, then it's shifted to the right, which means that the M's are surrounded in their second coordination shell principally by A's, and then that's equivalent to talking about a complex anion, although we never explicitly talk about complex anions. But it comes out to be math. If delta G is quite negative, it comes out to be pretty much the same thing. Over on this side, but it permits you also then to extend the model way over to the other side over here, and it also permits you to have this reaction shift back towards the left so that the second shell isn't all A pluses, and that way we can talk about the different trends, and then you can optimize the model as we normally do with the modified quasi-chemical model, whereas with the, as I said, with the complex ion model, this is necessarily always shifted to the right. The complex ions always have the alkalis in their second shell. You can't have any deviation from it. Okay, so let's explain sort of physically here though the trends. So in every system, all these systems with alkali chloride MCl2, as we move down, as the alkali goes from lithium, sodium, potassium, cesium, clearly the complexing gets stronger. The tendency towards the second nearest neighbor pairs gets stronger. Okay, how do we explain this? Well, let's suppose that we have lithium as a little tiny ion here. So we could have lithium out here, or we could have cesium out here. Okay, now remember the second nearest neighbor pairs are, second nearest neighbor interaction is a repulsive interaction. These are both positive ions, okay? So we're trying to minimize the repulsive interactions. If you have magnesium, the divalent ion, say magnesium, cobalt, whatever, 2+, is a small ion. If you put another magnesium 2+ here, a small ion, they're close together. Okay, and this is quite a strong repulsive interaction. So you're going to try to minimize the magnesium 2+, magnesium 2+ interactions, and you do this by putting the second nearest neighbor shell cesium. Now, if the second nearest neighbor shell is a big ion like cesium, then the next M2+ is way over here, so you really are minimizing the magnesium 2+. The MM interactions are being minimized by replacing them by a large, these are very weak. Okay. On the other hand, if you put lithium here, it's a small ion, then the lithium doesn't keep it away that much from the other magnesium, and as well, lithium-lithium interactions now are quite strong, and you're trying to avoid the lithium-lithium interactions as well. So if you look the whole thing down, or the other way, maybe looking at it is just if you have a whole lot of big cesium ions here, the cobalt can really grab in the chlorine. If you have small lithium ions, the lithium ions kind of compete with the magnesium ions for the chlorine and try to form their own sort of semi-complexes. But whatever, if you have great big ions out here, the magnesium tends to surround itself with chlorine, put the big cesiums, and that keeps the magnesiums apart from each other, and it tends to be more towards the ordering. So you always get this, as you have a small, the lithium ion being a small, it tends to be the small ions, magnesium 2+, the stronger, the smaller, and the more strongly charged the ion is, the greater is its tendency to form these complexes. So the lithium is kind of competing with the magnesium for its own complexes. Cesium has no tendency to do. That's what I like to look at it as, just the cesium, magnesium. It just maximizes your distance between your strong secondary, keeps the magnesiums away from each other. But certainly, if we treat these systems using the quasi-chemical model, this delta G for the quasi-chemical reaction becomes more and more negative as you move down. The lithium is almost randomly mixed. That is, there really is not much complexing in this system. The lithium and the cobalt ions or magnesium ions tend to be more or less randomly mixed on the second nearest neighbor site. So there's probably a slight tendency here. Now, we also see there's a tendency also, so that's how the alkali ion, how does the M affect it? And this appears to be, again, related to the size. If you have a small M ion, such as magnesium and so on, then you tend to have stronger complexing. If you have a big ion like lead, here's your lead chloride systems, you see you have the ordering, but it's not nearly as strong. Even in the cesium, it's not nearly as strong as it is in the other systems. And I think this is reasonable. As the M here becomes larger, it has less of a tendency to form these. The system becomes more ideal, the complexes are not as strong. And so the bigger the ion. So again, magnesium is strong, beryllium is very strong, calcium, you get very little complexing. As soon as you get down to calcium, you really, down in the alkaline earths, you really get very little complexing. Maybe a little bit if you take alkali chloride, calcium chloride, I don't have them on here, but calcium chloride, alkali chloride, even with cesium, tends to be pretty close to a random type mixture. But certainly strontium and barium don't have any real complexing effects. Okay, so as this M plus ion, M2 plus ion gets bigger, the tendency to the complexing decreases. Now the anion, chlorine here, also has the effect, and again, when it's smaller, you have a greater tendency to the complexing. So the fluorides are even more strongly ordered than the chlorides. Here we have the system with lithium fluoride. So even the lithium fluoride is more strongly complex. Here, potassium fluoride. So the fluorides tend to be somewhat more complex than the chlorides for the same thing. So potassium fluoride, magnesium fluoride is going to be stronger than potassium chloride, magnesium chloride, although not terribly much it seems, but the fluorides do tend to have greater tendency. When you get down to the bromides and the iodides, then you get these big ions, and with the big ions, it's just big, in general, the bigger the ions, all interactions are weaker. If you have a great big ions, the interactions are weaker. That's maybe just another way, if you don't even like this business about the cesium magnesium business. As you make A plus bigger, or you make the halogen bigger, or you make the M2 plus bigger, just all the ionic interactions are less, and so you get less tendency to form these ordering. Okay, so ordering, as you make A smaller, you make the halogen smaller, you make M2 plus smaller, you always have a higher tendency to ordering. Okay, so that's the divalents. What happens when you go to trivalent and tetravalent ions? And now things, so okay, and these systems here, by the way, on the right-hand side over here, on the right-hand side, these systems are still ionic. I mean, magnesium chloride is still an ionic salt, magnesium and chlorine. And the quasi-chemical model treats magnesium chloride as simply magnesium chlorine. Okay, and then you just, you have more tendency to form magnesium. And then you just have the model over here is the same, the magnesium A bonds are favored over the A bonds. But this is still completely ionic across the entire range. Now when you go to something like, when you start to go to higher valencies, like aluminum or say zirconium or something, then things get a little messier, because aluminum fluoride are not ionic materials. Aluminum fluoride is a molecular material, basically formed of AlCl3, 2 dimers, both in the liquid state and the gaseous state. Very volatile, same with the fluoride, and it's not ionic. But if you put aluminum chloride into potassium chloride, then what you tend to get is you tend to get AlCl4 minus complexes. And so over here on the basic side you have potassium, you have a model like that. Which again we can treat by the quasi-chemical model. I'm not writing this as a complex formalism, but you have a quasi-chemical model just as before. Aluminum forms through potassium aluminum. And so you tend to have your aluminum with your 4 chlorines around it, with the potassium in the next shell is the same thing. And this is an ionic over on this side, so it has a low vapor pressure because the bonds are strong ionic bonds, they're not weak van der Waals bonds holding the stuff together. And you have a low vapor pressure, you can electrolyze it and get aluminum out and this sort of thing. Over to here now, when you get past, so the minimum now comes at KAlCl4. Your phase diagram comes down very steeply here, okay, because the activity of aluminum chloride is getting very, very low because the activity of KAlCl4 is very high. Then as you go over to the other side, now it's more complicated because what's going on over here, because now you have a mixture of ionic and molecular and molecules. And really there's no good model for what's going on over this side. So what we generally do is we just blindly push the quasi-chemical model through anyway. We don't explicitly try to take account of the fact that somehow by the time you get over to pure aluminum chloride you're going to have molecules, and in the middle you're going to have kind of a mixture of ions and molecules. We just apply the quasi-chemical model across the system and we fudge it in with a lot of parameters. Okay, just to be completely honest about it. What this gives you, the phase diagram, looks like this, with two liquids here. There's some compounds in here, but this is basically how it works. The phase down, the liquid is here, goes down very, very steeply. This is a very low valley because you've lowered the activity of the KCl very, very greatly by complexing. Then on this side, so over here it's ionic, over here it's molecular, and in here it's whatever. And since, of course, the molecular and the ionic liquids have very different bonding and very different structures, they tend not to want to mix. Just like oil and water, you have different bonding, they don't mix. Okay, so the ionic region and the molecular region just don't want to mix with each other. So you get a miscibility gap. The way we model that is we model it with the quasi-chemical model. The delta G curve, that is going to look something like this. It's going to come down very negatively, come up here, and then have kind of a wiggle on this side with a minimum of 50% now. Okay, we model that with the quasi-chemical model. We put strong positive parameters over here in order to make the high miscibility gap. So the delta G for the KAl reaction, this is the quasi-chemical parameter. We expand that as a power series, A plus Bx plus, and then in order to get things up here, we'll have something like Cx to the 6th plus Dx to the 7th or something like that, which gives you a positive thing, but only over on this end. Can you read that? The delta G, in order to fit the Gibbs energy curve to do the optimization, we have delta G as A plus Bx plus Cx squared, whatever. Then we have a couple of powers which are quite high. X is x of AlCl3 to the 6th plus x to the 7th. We use high powers so that these terms only have some effect over on this side where x gets close to 1. If you're over on this side where the mole fraction of aluminum chloride is small, then these terms are very small and have very little effect. These terms are positive, and they give you the flip in here. We usually have two terms, one positive and one negative, because they have to kind of counterbalance each other. That's how we like to do it. Okay, but this is like really straight curve fitting fudging, because it isn't really a model, it's just forcing the quasi-chemical model to give you what you want. I mean, a quasi-chemical model is better, and certainly better than any other model I can think of at the moment, but it isn't really reflecting what's going on because things get more and more complicated as you get over here. This is a reason, too, to use a straight power series rather than a Redlich-Kister. You know, the Redlich-Kister power series is x1 minus x2 to the n. As I said, has the advantage of being always 0 at 50%, so it doesn't. Okay, it becomes kind of equal on both sides, but whereas normally if you use a power series, a term like x to the 6 is only important on this side. It doesn't have any effect over on that side. Okay, but in this particular case, that's what you want. You want terms that only affect this side, that don't affect the other side. If you use a Redlich-Kister x to the 6th term, it affects both sides. You don't want to do that. You want to kind of fit the left side of the diagram. Usually can be fitted with one or two parameters simply, and then you want to add parameters over here to give you this blip. But you don't want to start playing with these numbers and having to constantly change what's going on here. So in these cases, we find that these powers are better. Okay, so this is what happens with aluminum chloride. Similarly with aluminum fluoride, if you just replace this by fluoride, say sodium, if you put sodium fluoride and AlF3, then you've got cryolite, the bath for the aluminum Hall-Héroult process. And again, it consists, the aluminum fluoride consists of AlF3, 2 dimers, and it's the same general idea. Now it becomes more complicated if you really want to fit this thing properly. This is the work that Patrice did here way back when. If you take a system like sodium fluoride, AlF3, you have cryolite, a solid compound, Na3AlF6. And there's actually a solid compound in the system. Other compounds here as well. And then your two liquid miscibility gap over here in your phase diagram. Okay. And this led everybody to believe, since you do have an actual solid compound, solid cryolite, you're dealing in your electrolyte region over here, solid cryolite, to presume that in the liquid you had AlF6 complexes. Or in the quasi-chemical model, you would have your sodium aluminum, the ratio of Z would be 3 to 1. But when you really look at all the liquid data, the enthalpies, the activities, and all these things, there really is very little evidence for complexing around AlF6 composition. The complexing seems to be around the AlF4 in the liquid, even though there's a solid compound. There's no solid. In the chlorides, by the way, there is, in the chloride diagram, sodium chloride, aluminum chloride, there is a compound NaAlCl4, solid compound. And there is no solid compound Na3AlF, Na3AlCl6. There's no AlCl6 solid compound, there is an NaAlCl4 solid compound. In the cryolite system with the fluoride, you have a solid compound around AlF6, you don't have the solid compound around AlF4. Nevertheless, the liquid really seems to be better fitted with AlF4. In fact, to get a proper fit, Patrice has also added two complexes, AlF4 and AlF5, by a trick of talking about two kinds of aluminum, basically. There's tetrahedral aluminum and octahedral and pentahedral aluminum. And he gets a better fit considering two. He uses the quasi-chemical model with two different kinds of aluminum, so that, well, I won't go into the details. Okay, but the general point here for the is that when you're getting into the trivalent systems, the pure materials are not ionic, but they become ionic over on this side. And it does seem that it still seems to be the tetrahedral complexes that are important when you're dealing with trivalent stuff. I'm dealing mainly here, I'm talking about salts, I'm dealing mainly with the halides because the same thing with complexing that would apply to other salts like sulfates and nitrates and so on. But once again, these are big anions, and as I said before, when the anion becomes big, and then interactions become weaker, and you have less tendency to order it. So when you're dealing with other anions like sulfates, nitrates, and so on, with big anions, the complexing is generally very small. So it's usually the fluorides and the chlorides are where you really get the complexing here. These are small anions. Big anions, truly complex anions like SO4 and NO3 and so on, don't have a tendency to complex. They tend to be quite close to ideal. The same thing would be, this is now, we're treating all of this, we're treating it as ordering on the cation sublattice. The cations tend to order. The cobalt and the potassium prefer our preferential second nearest neighbors. This doesn't occur in when you go to the common cation system. If you go to something like NaF, NaCl, where you might consider that you might have ordering on the anion sublattice, like FF plus Cl, Cl forms 2FCl to form ordering. There's hardly any of this, again, because the anions are larger than the cations. There's not much tendency for them to order. Okay, so common cation systems that have the same cation but different anions, there's no great tendency to short-range ordering. All right, so now when you get to systems that are tetravalent, such as zirconium, you go to something like ZrCl4. ZrCl4 is again a molecule, and now what you find is you take something like KCl. We gave this for a homework problem. ZrCl4. Again, you're going to have a phase diagram that's going to look something like this. Over here you've got molecules. None, not ionic. You're going to have two liquids. And over here you're going to have ionic, and it's going to be potassium, chlorine. And in this case it's ZrCl6. Can't be ZrCl4 because that's not charged. It'll be ZrCl6. Possibly ZrCl5, but ZrCl6 seems to... Now again, it could be treated by the complex ion model, or if you want to treat it more correctly, you treat it with the sublattice, with the quasi-chemical model. The quasi-chemical model really only goes over a ways until you start to get the molecules, and then if you want to fit that side, you got to fudge it in again. Okay, so other things like niobium, but not enough data, but when you have highly charged cations, niobium can have 4 and 5. You could have NaCl5, you might have NbCl4. Again, the tendency is to form strong complexes because these are highly charged. Zirconium is a highly charged. It's relatively small, but it also has an extremely strong charge. Okay, when I said the size affects it, also the charge affects it. The higher the charge, the greater the interaction. So remember, I said the size of the ion is either the alkali or the chlorine or the negative ion or the M2 plus ion or whatever gets larger, the interactions get weaker, the tendency to complexing goes down. But this also it goes with the charge. As you have ions that are highly charged, like aluminum 3 plus or chromium 4 plus, have strong interactions because they have higher charges. So as the charge goes up, there's a higher tendency to have these complexing interactions. So things like niobium, zirconium, aluminum are strongly complex. The aluminum chloride is less strongly complex than the aluminum fluoride system, and so on, because the fluorine is small. Okay, so as the ionic size goes up, complexing energy goes down. As the ionic charge goes up, complexing tends to go up. In these simple molten salt systems, the only ones where then you really have a great much complex tend to be the fluorides and the chlorides. All the other anions tend to be large enough that you can put in you can put in quasi-chemical model and short range ordering, but it tends not to be such an important factor. Okay, so that's my discourse on molten salt chemistry. Alright, now the one class that people don't even call it molten salts, but they really are molten salts, are the molten oxides, particularly the silicates, known as slags or magmas or whatever. And these are, start talking about this now, and I put in a new file the other day, 49. This is actually a talk I gave a while ago, well, May 18th, 2010 to be exact. So there's some things in here that are kind of irrelevant, but this is introduction to the structure and thermodynamics of liquid oxides. Okay, so we just kind of go through the slideshow. I won't talk about too much mathematics here. So liquid oxides meaning slags, and if you're a geologist, a magma. It also applies to glasses. Oxide glasses are super cool liquids, if you like. So we're talking about glass. Glass melts is what the glass people call them. Okay, so okay, if you have basic oxides, these are ionic oxides. Ionic basically means ionic. Something like calcium oxide, this is really just like a molten salt. Calcium oxide is calcium ions and oxygen ions. And if you have a system calcium oxide solution, CaONGO, it's going to be like KCl and NaCl. These are no difference, you just treat these like molten salts. These are molten salts. Liquid calcium oxide is very fluid. It's this very fluid like sodium chloride, which is about the fluidity of water, same viscosity as water. It's a good ionic conductor. CaOMgO or CaOFeO. If you mix these oxides here to form a solution, it's an ionic solution with the two sublattices. You can treat it the same way you would treat sodium, potassium, chlorine, fluorine, or whatever. And with the charge difference, it doesn't really matter. The sodium and potassium, again, you use the Temkin model. The sodiums would, in the solids, in the liquid state, the sodiums would exchange with would substitute with the calciums. Potassiums would substitute with the calciums, and the local coordination would change to keep the local charge balance. Use the Temkin model, and you just use exactly the same equations that we've used for the molten salts, NaCl, MgCl2, and so on. Now, when you get to what they call acidic oxides, these are network formers, is what the metallurgists call them acid oxides. The ceramic people call them network formers, whereas the calcium oxide, going back here, we call these, the metallurgists would call the ionic oxides basic oxides. The ceramists would call these, ceramists or glass people would call these network modifiers. I'll show you why. These are network formers or acids. Okay, silica tends to form silica. The most important ones are silica, and let's say germanium, which is in the same group, tend to form a tetrahedral network. Boron tends to form a trigonal network, and P2O5 forms a complex, means we don't really know what it does, but it's a network. Here's your silica network. In 2 dimensions, it's actually a 3-dimensional thing. Every silicon is bonded to 4 oxygens. Okay, and this is completely, no matter what you do when you have silicon in an oxide, it's going to have 4 oxygens around it at the corners of a tetrahedron. I've drawn this in a plane, but this is really towards the corners of a tetrahedron. Okay, and this is completely justified by spectroscopy and all sorts of things. Every silicon has 4 oxygens around it. No matter what you add to this now, calcium, magnesium, whatever, you aren't going to break. You're not going to wreck the fact. You're not going to change the fact that the silicons are bonded to 4 oxygens. And these, as far as I'm concerned, are covalent bonds. I mean, they may have some slight polarization to them towards the silicon, but for all intents and I do not. I think to call that a silicon 4+ is just, well, you could call it that, but that's only the valence. These are covalent bonds. They're sp3 orbitals towards the corners of the tetrahedron, period. That's all you find. Okay. Now, then, each silicon in SiO2 is bonded to 4 oxygens, which are shared by a neighboring silicon. So this is what we call an oxygen bridge. And this is a covalent bond through the oxygen bridge. You got to imagine this in 3 dimensions. This is everything towards the corners of the tetrahedron. And this actually then forms a diamond lattice with the silicons on the nodes, the sites of the tetrahedral lattice. So it's actually like diamond. You can imagine the diamond silicon, metallic silicon forms a diamond lattice. And at least in the cristobalite structure, you just put the silicons on the diamond lattice, but you put oxygens between them. Okay, so. And you can imagine that this is not ionic, because these things are not mobile. These are covalent bonds. It's not ionic. It's extremely viscous, because covalent bonds are directional. Ionic bonds are not directional. Doesn't matter. The strength of an ionic bond just depends upon the distance between the 2 ions. Okay, but here it depends very much on the angle. If you change this angle, if you make this angle less, then the energy goes way, way up, because the 2 oxygens are coming next to it. The electron clouds come next to each other. Okay, so you can't change the angles. So these are tetrahedral angles. You can't start changing the angles without greatly increasing the energy. So the thing tends to be a very rigid structure. So it's highly viscous, like way, way viscous. It's 20 orders of magnitude more viscous than in Quasi than is calcium oxide, for example. It's way more viscous than, say, honey. This is a really viscous stuff. And it's not an electronic conductor. It's not an ionic conductor either. It's a network former. Germanium oxide will be the same thing. Just germanium replaces silica. Boron oxide. Boron is a member of group 3, so this is more complex, but the boron then tends to form sp3 orbitals. So you'll have the boron, it'll have 3 oxygens at the corners of a tetrahedron. And there's another pair of electrons up here where the 4th bond would be. And these tend to then form kind of a puckered plane, a boron here, then another boron up here, and another boron down here. This can be very complicated, but it is a long network. And some boron can also be tetrahedrally coordinated. I'll show you a bit later. Okay, but you still end up with B2O3 forms a, B2O3 ends up forming a network, but it's a bit more complicated than this because of its trivalent. Okay, so that's the structure of silica. Now the reason basic oxides are called network modifiers is now we're taking, modifying the network by basic oxides. So we're adding, say, calcium oxide or sodium oxide to pure silica. We're adding a small amount. So here we're still very much rich in silica, so it's very much rich in SiO2. We're adding a small amount of calcium oxide or sodium oxide. So what happens is the calcium oxide, the reaction is basically your calcium oxide contains oxygen ions. Okay, this reacts with your silicon bridge. So here we have a silicon, oxygen, silicon. So this is a silicon oxygen bridge in pure silica. And it breaks the bridge. So what happens is you have a calcium ion is formed, and this oxygen breaks the bridge and attaches itself up like that. This oxygen goes into the bridge, and you have the two oxygens here. Now these then become sort of single charged. Okay, so this is your bridge breaking reaction. Okay, so your calcium ion puts itself here, and the oxygen ion goes here. Now this then is a positive charge. This now is a region of negative charge, because you have negative charges sort of here. So the calcium will tend to place itself next to this is called a broken bridge, will tend to place itself next to the broken bridge, because this is a region of negative charge, this is a positive charge. So every time you add a calcium ion, it's also written this way. O0 is a bridge, a neutral oxygen. O2 minus is the oxygen ion that came from the calcium, forms two O minuses, which are broken bridges, broken bridged oxygen. This is an O minus here. This is an O0, and there's hardly any O2 minuses left because this is a very strong reaction. All the O2 minuses have. Okay, and the calcium tends to stay next to the broken bridge. If you add Na2O, then Na2, you need two sodiums to break the bridge. Na2O Na2O bridge forms two sodium ions plus your broken bridge. Okay, so your broken bridge, here's your broken bridge. These are both O minuses, so this is a region of 2 minus, so the two sodiums are going to tend to stay next to the broken bridge by the charge attraction. So what we're doing is we're breaking up the network. So as you continue, if you start with pure silica and you continue to add calcium oxide to it in greater and greater amounts, every time you add a calcium you break a bridge. It's like, imagine snipping the bridge. And at a certain point, this whole structure is going to sort of collapse and start to become mobile. You're going to get chunks of silica start moving around, so the viscosity drops way off until you get over to the other end, where you get over to the end of pure CaO, and now all the bridges have been broken. Okay, so you're going to see a huge drop. At first you don't see much, but then you start to see a huge drop in the viscosity, and you start to see an increase now in the ionic conductivity. Okay, you have these cations you now have these mobile cations, which are charge carriers, and as you get further and further over, you're going to get negative chunks of silica lattice, which can also move around as well. So let's look at the system. Okay, so let's go across the whole system now from composition. Let's start liquid. We're going to have complete miscibility from calcium oxide right over to silica. Okay, so over here at the pure end in silica, we have a three-dimensional network, which is what we just talked about here. I don't show it here, but in this region, as you start to move over this way a little bit, adding 3, 4, 5, 6% of calcium oxide, then your structure is very much like this. You still have the three-dimensional network, but you're starting to break it up. Okay, so in this region here, you have a three-dimensional network which is starting to be broken up. Before we do this, let's go back to the other end. Here at calcium oxide, you just have calcium ions and oxygen ions. And now, as you move in this, you're in the basic region, and now basically all the bridges have been broken, and you have isolated SiO4 orthosilicate ions, which have SiO4 minus ions. Okay, all the bridges have been broken, but the silicons always have 4 oxygens. You can't get around from that. So this is an SiO4 complex ion. In this case, it really is, I mean, these are covalent bonds in here, so it's like SO3 or something. It really is a covalent ion. Okay, so here we have mainly calcium, oxygen, and SiO4s. Now, the maximum for this would be Ca2SiO4, where you have calciums, SiO4s, and no oxygen ions. Now you can't go beyond that without doing something. Okay, so what you do is what happens is you start to, at first, you start to get dimerization. So you get polymers. So you have the silica. Here you have the silica. The silica has 3 oxygens. So it has 3 oxygens. If these were orthosilicates, they would be 4th oxygen, but what they do now is they share the 4th oxygen for a bridge. So you have a dimeric ion. So this would be Si2O7. Where you have 8, 14. That's 14. Is 8, what, 6 minus? Okay, a dimer. This then reduces the amount of oxygen. You need less now, it's 3.5 oxygens per silicon rather than 4, so you can go over a little bit further. As you go over, add more and more silica, then you start to get more. So you get another bridge here, now you start to get a trimer. So you get a linear chain. You get trimers. Okay, so this has also been, I'll talk about some of the evidence, but as you move further to the right here, you don't have enough oxygen to have everything SiO4, so you start to get Si2, Si3, SiO4 chains. So you end up with an area which is linear, a region of linear, basically linear polymers. And now the viscosity starts to go up because these chains start to, it's like, you know, a long chain polymer like nylon is viscous because the chains tend to get tangled, they're not so mobile. You also now get branched polymers. As you start to go a little bit higher, you have the linear polymers. I won't put the oxygen in, but a linear polymer would be like this, where you have oxygens in the middle. A branched polymer, you can start to go off this way as well, so you start to get linear and longer linear and branched polymers. Then you also can get ring polymers as you go even further. And a ring polymer can form a lot of silicons along like this to form with these covalent bonds, and these bonds here go to the oxygen ions. And then the ring polymers start to converge into 3-dimensional networks, big iceberg chunks, and so on. Okay, or going the other way, we're starting here, we start to break up the network. As we break up the network a lot, we start to form big icebergs which can move through. These icebergs become smaller and smaller and smaller, and eventually end up becoming little chains and small polymers, and when you get over on this side, we end up at the limit with the completely busted up SiO4s. So as you move across here, the viscosity goes up. Here the viscosity stays pretty well constant and then goes up like crazy by 20 orders of magnitude. The ionic conductivity is the same thing, it's quite high here and then goes way down. You get to the other side. The activity of silica will be very low over on this side, and then go up quickly on this side. Calcium oxide is just the other way around. All right, and that's basically what you get with these things. Okay, here's your branch. That's your linear chain, and here's a branch chain polymer now. Okay, notation that we use as we talk about units: Q3 units, Q4 units. A Q4 unit is a silicon that has 4 oxygen bridges around it. So this silicon is bridged to 4 other silicons. So that's called a Q4 silicon. This silicon here is bonded to 3 other silicons by bridges. Or let's say this one, this is bonded to a silicon here, and here, but this is a broken bridge, so this is a Q3. Okay, you could have a Q2 silicon will be a silicon that is bonded to two other silicons by bridges, but the other two bonds are broken, so that's a Q2 silicon. You have a Q1 silicon, and the SiO4 4- ion is a Q0. So we can have from orthosilicates, which are Q0s, up to Q4s. These can be measured, the compositions can be roughly measured by NMR, nuclear magnetic resonance. And this is kind of, in fact, what we get here. The Q0 species, of course, are 100% Q0 species. This is lead oxide silica now, because it's a lower melting point, they can measure the stuff. Q0s, as you see, go way down. There's still some Q0s beyond 33%. I mean, in the simple model, this would go way, way down to here, and then it will start to dimerize. It starts to dimerize before you get to 33%, because there's equilibrium. The Q, so you have the Q0, which are the discrete SiO4 ions, tend to go down. They go down to 0. The Q1s, which are basically a silicon bonded to one other silicon, like dimers, if you like, or linear chain dimers, they go up and then they come back down again. The Q3s are a little bit further over, and the Q4 species then go up until you have 100% Q4 species over here. The NMR gives you the nuclear magnetic resonance, tells you sort of the from the spectrum you can tell the surroundings of the ion, you can tell how many silicons it's from. The silicons give you the points are experimental points. The lines were lines that we got from our quasi-chemical model, which was kind of interesting. Because we did I'm getting ahead of myself, but the quasi-chemical model was done completely from thermodynamic optimization. We didn't use this in the thermodynamic optimization. We did the thermodynamic optimization just as usual, using the quasi-chemical model from the thermodynamic properties, the phase diagram. And of course, once you've got the thermodynamic model, you can calculate the number of these species, and they fit quite easily. This is system sodium oxide silica. Actually, you can see in the lead oxide silica, well, maybe you can't. Okay, this would be the Q4 species that were measured by different techniques, by nuclear magnetic resonance, by Raman, by molecular dynamics calculations, by NMR, by different people. They measure the number of Q4 species, and you see that it does tend to hardly any Q4 species until you get into the acid region, and then it starts to go up very, very rapidly. Okay, so how are we going to treat the system? We're going to treat the system the same way we treated the systems I just talked about, KCl, MgCl2. One sublattice quasi-chemical model. Here we had KCl, MgCl2. We had over on this side, we had potassium ions with MgCl4 ions. Just take one charge off this, replace that by calcium, replace that by chlorine, replace that by MgCl4, and you've got the complex ion model on that side. We're going to treat it using the quasi-chemical. Here I said we treated this system using the quasi-chemical model with Kk plus magnesium, magnesium, forms 2K magnesium, second nearest neighbor bonds. Okay, you see the same thing here. We're treating this now as a silicon, and we treat this the same way. We treat silicon and calcium, and the second nearest neighbors then are silicon-calcium bonds. As I said, you can consider that to be a complex ion, or you consider it to be simply silicon prefers to have calcium as the second nearest neighbor. Okay, so we're then treating this, the calcium silica system, we treat it as calcium, I don't want to put a charge, calcium, silicon, oxygen. We treat it as a one sublattice model, exactly the same as this, a one sublattice quasi-chemical model. But we have a very strong tendency for calcium-calcium plus silicon-silicon forms 2 calcium-silicon. The delta G is extremely negative for that reaction. Okay. And so in the basic region, the calcium-silicon bonds are simply these, calcium-silicon, second nearest neighbors. In the acid region, it is still saying that you tended to have a calcium silicon. In the acid region, we still have a very strong tendency to form calcium silicon. Here, this is your calcium silicon. Okay, the silicon bonds tend to be broken up and replaced by calcium silicon bonds. Breaking up the silicon bonds and forming calcium silicon bonds. Okay, so on the acid side, this could be looked at as a network modifying reaction. It's the same thing. Okay, the O0 plus O2 minus forms 2O minus. You could think the O0, an O0 is really a silicon-silicon bond, and O2 minus would be basically, if there were two calciums, they'd be separated by an O2 minus, but there just hardly any of these because it's so far. And the O minus could be considered to be a calcium silicon, two calcium silicon pairs. So your O0 plus your O2 minus, O2 minus, or your O0 is your silicon-silicon bridge, your O2 minus is your calcium-calcium pair, which is completely destroyed, and your two O minuses are your two calcium silicon bonds here. So we're modeling, and this again is a very negative reaction. So on the acid side, the quasi-chemical reaction here tries to mimic the charge, the network modifying reaction. On the basic side, it mimics the complex ion formation, the orthosilicate reaction. So right back again, although it's a very complicated system, we're using the same one sublattice quasi-chemical model that we use for something like aluminum calcium, where you have your Z, your ratio of your Z now in the calcium-silica is again 2:1, because you want the minimum at 33%. Sodium silica would be 3:1 because you want the minimum at Na4SiO4. So here we have the silica plus MO forms M2SiO4. This is your complex forming reaction, if you like. Or this could be considered a silica bridge plus an oxygen silicon plus O2 minus forms your broken bridge. Or, as I said, this reaction is sometimes written this way as the bridge breaking reaction. You break the network modifying or the bridge breaking reaction, you have the bridge plus the oxygen ion forms a broken bridge. So for this reaction, the delta H, the delta G are basically your quasi-chemical parameters. The enthalpy of mixing looks as you would expect. This is the enthalpy of mixing in these basic oxide systems: magnesia, calcium, strontium, barium. Strong minimum around 33%, as you would expect, because that's where the complexing is. So that's the 33% is the Ca2SiO4 composition. This is the same trend now as we saw in the salts I showed you with alkali chloride, magnesium chloride. If you went down lithium, sodium, potassium, rubidium, cesium, you got further and further down. This is the same thing. Now you're going down the alkaline earth series. The magnesium is a smaller ion, so you get to the bigger ions down here. The barium, it tends to give you a stronger tendency to the complexing. Okay, so you have a stronger complexing. Actually, I think I said that wrong when I said the size of the ion. If you're talking about this alkali ion, the network modifier, the bigger the ion, the more the complexing. If you're talking about the M ion, it's, well, you understood that. I don't know. The entropy of mixing is the same sort of thing. You see your minimum and your entropy around 33%, as you might expect for the and again, it tends to be stronger. The calcium, strontium, barium has stronger complexing than the... See, now the entropy mixing actually seems to go negative. It really does go negative. All right, but over here you notice this thing comes down very negative, and then you get this positive flip up here. It tends to curve around like that. You can see that here very, very slightly. You see a positive flip. If you put a ruler along here, you'll see that you're going to get a miscibility gap on that side. A very strong negative to form the complex, and then it tends to become somewhat positive over here. And why is this? It's the same thing as I talked about in the system with, say, sodium chloride, aluminum chloride. Where I said in the system, sodium chloride, aluminum chloride, if you had KCl, AlCl3 over here, you're going to get an ionic region. Okay, but then over here you get a miscibility gap because this is a molecular region and this is ionic and they don't want to mix too much. The same thing happens here, but for different reasons. Pure silica is not, pure SiO2 is not molecular, but it's a covalent structure. Very different from the ionic structure you get over on this side. Okay, so they really don't want to mix. Okay, so what you end up with is you get these miscibility gaps. And there's your phase diagram. Here's your calcium oxide silica phase diagram, and you have this miscibility gap. Because over here you have this ionic. Here it's ionic up to 33%. Then it starts to become more polymerized, but it still is more or less ionic. But over on this side, it's quite covalent. So you don't want to mix, so you're going to get a positive deviation, which tends to give you two-phase miscibility on that side. Very much like KCl, AlCl3. So when we're modeling this, the heats of mixing then are modeled, as you see, the heats of mixing have a, they don't come down and come back up, they have this tendency to have a peak over on that side. And we model that then with the quasi-chemical model by putting in, as I said in the other system, the delta G has some positive terms. So we have, this would be your delta G of your quasi-chemical model for the calcium silica system. We would model this as, let's say, A plus B x silica plus, you might have a C, but then you would have D x silica to the 6th plus E x silica to the 7th, very much as I said with the aluminum chloride system. Because this models, these first two terms model the basic side, which is quite easy to model, and then you have strong positive terms here, which give you the miscibility gap. Okay, and we make these high terms 6 to the 7th, so they affect things only over on that side and don't affect much on the other side. That's why it's better. People say, why don't we use Redlich-Kister expansion in our quasi-chemical model for the silicates rather than using the polynomial? And the reason is, with the Redlich-Kister, which would be something like x silica minus x calcia to the 6th, it would have an effect on both sides. It's symmetric around 50%. You're trying to fit this and you'd be messing up this side. These terms here only really affect this side. Besides, you want these terms to have something to do over here, so you want a high power. So this is generally what we do in these systems. So again, the quasi-chemical model is only kind of an approximate thing for the right-hand side. But in many ways, I think it's better than with the aluminum chloride because it really does model. On one side, it models the complex formation. On the other side, the silicate basically for complex ion formation. And on this side over here, it more or less models the network modifying where the calcium oxide is clipping the bonds. But the model is the simple one sublattice polynomial model, or quasi-chemical model, with the Z ratio to be 2 to 1. There's your calcium silica. This is in fact our optimized. Our optimized Gibbs energy at 1750 Celsius. 1750 Celsius is here, so you're inside the miscibility gap. You can see how very sensitive this is. Now, I mean, you know, when you have the miscibility gap, you have to have this positive curve, but look how very slight, very, very little energy is causing the, if you see what I mean, this Gibbs energy, I'm going to exaggerate it, the Gibbs energy curve actually looks like that, and there's your miscibility gap. Okay, but this is a very, very small distance, which you can hardly see on this scale. Very, very, miscibility gaps are very, very sensitive things. A few hundred joules and you've got your miscibility gap. So this is all, this little flip here is given by these terms, these x to the 6th and 7th terms on this side. So you have like, the minimum here is like 65 kilojoules, extremely negative. But what's causing this miscibility gap is a few hundred joules. Okay, so Now, people say, why don't we have a more sophisticated model that takes into account the pairs and the trimers and the dimers and so on? The thing is that it becomes impossible to treat the thing mathematically at that point, and because we've had really good success with this model. But now I'm going to go back. So, okay, what we do is we took this model for the lead silicate system, and we fitted all, this is, I said this earlier, and I'll explain it in detail. You take the PBO SiO2 system, we took all the thermodynamic data, the phase diagram, and we optimized it, just the thermodynamic data, to get the parameters of the quasi-chemical model. So that gives us, now that once you have the parameters of the quasi-chemical model, you can now calculate the probability fraction of all the pairs. Okay, so we have the quasi-chemical model. This permits us to calculate the fraction of silicon-silicon bridges. These are silicon-silicon, this is a silicon bridge. Okay, after we've done the optimization, got the parameters, we can go back and we can calculate from the model, of course, gives us the pair fractions. So the silicon-silicon, remember, a silicon-silicon is a silicon bridge. Okay, so the quasi-chemical model, using the model, permits us to calculate the probability of a silicon being bridged to a neighboring silicon. Okay, now if you know the probability of a silicon being, if I know the probability of silicon being bridged to a neighboring silicon, I can do a little mathematics, and I can calculate the probability of any silicon being a Q4 or a Q3 or a Q2 or a Q1, just from a little mathematics in the structure, okay? So you're going backwards. We're using the quasi-chemical model from the thermodynamics to calculate the bond fractions, and so we can back calculate the Q4, Q3, Q2, and Q1 structural units. And then we compare that to the NMR, and it comes out not too bad. Now you don't going to expect this to be right on for something that's, the model is obviously not super sophisticated, but I mean you can see that we're getting not too bad representation. The Q4s come up like this, we got this, the Q3s were here, they had this. Okay, but I mean for a model that's based entirely on the thermodynamics, plus I don't, you know, the NMR is not all that. But we're getting certainly this one, actually the green ones came out kind of like that. So this was calculated after the fact. We did not use these data to do the optimization. I think we could have used these data to help us in the optimization, but we didn't. So this gives us some faith that we really are, like this isn't just, quasi-chemical model has some basis in reality. This was, again, this was the Q4s in the sodium silica system, the NMR results, and this was again calculated by us beforehand without using these numbers, without using these data. I find we're getting a pretty good fit to the thing. If your calcium-silica system looks like that, if that's your Gibbs energy, it's almost two straight lines, so you can imagine the activity of the Gibbs energy, the chemical potential of you rotate a tangent around this, the chemical potential of calcium oxide is this intercept, so it's going to be almost constant and then go very, very negative. And if you just calculate this back, this would be the activities. I mean, the activity of calcium oxide just goes zipping right down to virtually nothing here, and the activity, well, it's straight here because it's a two-phase region. And the activity of silica drops like to 10 to the -10th or something down. So that's what I said. The phase diagram, if you didn't have, you have the miscibility gap here because the liquid, the ionic region and the molecular and the covalent region don't like to mix terribly much. Here you do have some compounds. In this particular case, the orthosilicate Ca2SiO4 solid compound does correspond to the minimum. You see this liquid, this is dropping quite quickly on this scale, but this is several hundred degrees. Were this compound not here, if you just take this compound out of your fact stage calculation and just continue to calculate the metastable liquid as it drops way, way down. Okay, because the activity of calcium oxide is going virtually to zero. Okay, so these diagrams, well here you can see it over here too, the diagram, these kind of diagrams are characterized by very negative deviations on this side, which makes the liquid is very, very low. You're lowering the liquid is from 2600 down to 1400. Then quite flat over on this side with miscibility gaps. There's your sodium silica phase diagram. In this case, we don't have a miscibility gap, but you can see you have a tendency to demixing. the S-shaped liquid is. If you calculate the metastable phase, if you took the solid phase out, you would find a metastable miscibility gap down here. Liquid-liquid miscibility gap down here. Which you can realize, you can actually do this, you can suppress the formation of silica because it's extremely viscous. In fact, if you cool this material, it forms a glass. It doesn't form to get the crystalline, you got to wait a long, long time. Okay, so if you cool it down, you will in fact see the two liquid miscibility region, which is down in the glass region. It's a super cool liquid, very viscous at that point. This I won't be talking about this, but I said we can calculate the probability of a using the quasi-chemical model. As I said, you can calculate the probability of a silicon pair. That then permits us to calculate the probability of Q1, Q2, Q3, and Q4 species. So we tried to do this. This is what we've been doing for several years here in the fact-state slag viscosity model. In the fact-state slag viscosity model, we're trying to relate the viscosity to the structural units that are in the material. So as the number of silicon-silicon pairs goes up, you would expect to find the viscosity going up. But the viscosity goes up so precipitously if you go from calcium to silica, if you plot the log viscosity going from calcium to silica, even the log viscosity goes up like that. I mean, extremely fast at the end, by orders of magnitude. Thing goes up. So the Q4 species. This is the concentration of Q4 species, but that does not go up. The viscosity curves don't go like that. Even log viscosity curves tend to go very much like that. So what's happening, the point is the viscosity goes up because you get these big chunks of silica. You get these, this sort of thing. You get these big chunks, or even bigger than that. As you're starting to break up the network going this way, you get like big islands of stuff. And the viscosity only goes up when you start to have a large interconnected system. Just having a few dimers and trimers and things, that doesn't do an awful lot for increasing the viscosity. The viscosity only goes up when you have large clumps of these things. Okay, and so what of course it's going to depend upon clumps of 15, 16, 17, 18. What we did is we just took one kind of clump and we said the probability of having 40 silicons all joined together. Okay, now I know there's all sorts of geometry with that, but it doesn't matter. We just simply took basically X silicon to the 40th from the quasi-chemical model as a model of this. And we found that corresponds very nicely with the viscosity rise. It's a simplified way of modifying the whole thing, talking about when the interconnectivity of the silicon network becomes great enough, the viscosity will rise. And it rises more or less with 40, 30, something like that. And so we use those as the structural units when we were modeling the viscosity. We find quite nice. Can't go into the viscosity papers here with you, but basically, though, we start with the quasi-chemical model, which was optimized from the thermodynamic data. We use the X silicon-silicon pairs that have been calculated, and then we use that as the parameters in which we're using as our concentration unit for the viscosity model. It seems to work pretty well. Okay, that is the basics of. I won't talk about this. There's not too much left to talk about with slags, but I shall consider the okay, let's leave it there. Okay. For next Tuesday, I should give you some homework. That's examen final, number 4. These can all be found in the file number 30. And there's a 1999 exam, numbers 4 and 5, and that can be found in the file 34. So that will be for next Tuesday.